Professor Nguyen is still out of town, so that's why I'm giving a lecture today. But he'll be back by next lecture. So by the way, this is homework 1. Let me pass it. They are basically questions taken from your textbook, Gray and Meyer, and your covers, the fundamentals discussed in these several lectures. So just a brief review of 105 stuff. So I'm sure if you guys look at the lecture notes and also read chapter 1 of the textbook, you should be able to finish it like that. It's pretty easy, and just to warm yourself up. And it's due, I guess it's February next Tuesday. All right. So I think last Thursday Travis went through some of the BJT fundamentals. I think he almost finished up, just except some leftovers. So this lecture I will finish up the BJT fundamentals and briefly talk about some other parasitic of BJT that we will see in the small signal model. And after that, I will start a MOSFET. And I don't think I can finish up MOSFET this time. So Professor Nguyen will finish it up next lecture and start the inspection analysis. All right. So I guess last time you guys have already seen. Let's take a look at a small signal model of MOSFET, BJT again. Here it is. So B, E, and C, base, emitter, and collector. Between base and collector, there's a C mu. There's a capacitor. I guess Travis already introduced that. Now mu, and now first I would like to talk about is C pi, which is the capacitance between base and emitter. So to understand or calculate C pi, first let's apply a voltage between base and emitter. Then you think about how does the charge change. If you know how the charge changes, then you know how to calculate capacitance, right? So apply voltage across B and E, and because this is an NPN, by the way, because there's a PN junction first between B and E. So the depletion layer changes due to the voltage across, right? And you think of the depletion layer here as the two plates of a capacitor, and once the capacitance is equal to epsilon A over D, right? Once the width of the depletion layer changes, capacitance changes. And this is the first part of C pi. And C pi, so this part is called junction capacitance. It exists on every PN junction. To calculate that, I think you've already seen the equations. Here we just rewrite it again. Cj equal to Cje over 1 plus VEB over phi naught to the power of m. And VEB is in your textbook is 1 minus, but it uses VBE. So just to pay attention to the sign when you calculate it. And phi naught is the built-in potential of the PN junction. Let's see. So intuitively you can think of it like that. When you apply the voltage across B and E, when you apply a plus voltage, a plus voltage, how does the depletion layer change? It shrinks or increase? It's forward bias. Shrinks, right? So the distance between the two plates of the capacitor shrinks. Therefore, the capacitance goes up. Right? In this case, it's VEB, so it's negative sign. If you write it, if you use the equation in the book, it's 1 minus VBE. VBE increase, denominator shrinks, and then so capacitance increases. So that's the one easy way for you to remember this equation. And Professor Nguyen also mentioned CJE, VJE, MJE, those are the variables that you're going to need to input in SPICE model if you want to simulate this device. And so this is the curve between, of CJE versus VEB. And at this part, it follows well with the equation. But as you can see from the equation, at a certain point, at a certain value of VEB, the CJE will go infinite. But that's not the case in reality. The reason is once the CJE becomes very large, then the diode current becomes very large. In that case, the assumption of this equation doesn't hold anymore. So in order to calculate the capacitance after this point, you need some more complicated physics models, which is not covered by 140. I don't think 105 talk about that either. All right, so this is Johnson capacitor, one part of the CPI. Another capacitance in CPI is called diffusion capacitance or base charging capacitance. And why there's a CB in there? Because when you apply a voltage again on base, there's it will cause the minority carrier charge to change, which is electrons in base. And because of the charge neutron neutralization requirement, there's a certain amount change of electron, and there's an equal amount of change in holes, right? And which is the major majority carrier in base, and the majority carrier and the hose is supplied by the base lead. So in other words, you apply the voltage to the base, and that requires the supply of charge, and that results in the input capacitance, right? Capacitance is always related to voltage and charge. And to calculate CB, another way to look at CB is, since we can calculate CB using Q over VBE, right? Q is the charge change due to VBE change, and QH is equal to QE. And in order to calculate QE, we have to introduce this parameters tau f, which is the average time spent per carrier across the base. And tau f, I think you've seen this in Travis derivation. The tau f. Tau f is equal to QE over IC. IC is the static current of collector. And going through, so this is IC here is large signal. So if you apply small signal on both sides, it becomes small QE and small signal IC. And since CB is equal to QH over VBE, and QH is equal to QE, so you plug in this equation, you end up getting CB equal to tau f times GM. And we can also rewrite GM to IC over VT, right? IC is the bias current, and VT is KT over Q. So we have the conclusion: CB is proportional to your bias current. The larger the current, the larger the CB. So combining these two parts, CB and CJE, we have this final expression for CPI. All right, let's capacitance between emitter and base. Now, between the base and collector, there's not just a capacitor. There's also a resistor, which we call R mu. And why there's a resistor is there? Again, apply voltage between collector and base. So when you apply voltage across a collector and base, the depletion layer increases because you're reverse biased the PN junction, right? And once your depletion region increases, your base width decreases, and so there's less recombination current there, or there's of course less minority carrier charge, so less recombination current, and so therefore, when you increase VCE, you decrease IB. So what is that? That is a resistor, right? Voltage change induces current change. That's a resistor. So seeing that, now we start to calculate R mu. So by definition, R mu equal to IC. R mu equal to VCE over IB, right? Here. And there's not a direct relationship between, according to what we have learned from equations, there's not a direct relationship between VCE and IB. So R mu equal to VCE over IB, we can rewrite it to VCE over IC times IC over IB, right? Since we can relate VCE to IC, and we can relate IC to IB too. So VCE divided by IC is equal to RO, is output impedance, and IC over IB, which we all know is beta, current amplification ratio. So R mu is equal to beta times R naught. And this is not quite accurate still, because we assume all the IB is recombination current, which is not completely true. For MPN, only 10% of IB is recombination current. So your actual R mu is about 10 times larger than beta R naught. And for other devices like lateral PMP, which in those devices recombination current is more significant. So the real R mu is closer to what we have calculated here. So okay, so yeah, so here's the range of R mu you can get in real devices: 2 to 10 times beta naught R naught. 10 times is closer to MPN devices, and 2 is closer to lateral PMP devices. All right, so after talking about C-pi and R mu, I think we have gone through all the parasitics that you have seen in a small signal model. So this is the cross section of a typical MPN BJT with all the parasitics shown, almost all. So let's see. So for MPN devices, you use P substrate. Then you dope the P substrate with to form N well, which forms the collector region. In this N well, this is N well. This is all collector here. You dope a P region to give you the base, and in the base you dope a N region, heavily doped N region, because it's emitter. It needs to emit electrons out, right? So you heavily dope it, a region which forms emitter. And by the way, the plus here means heavily doped. You in semiconductor you see plus and minus on top of N and P. That means the doping level. All right, so the active region is right underneath the emitter, NPN, right? Emitter, base, and collector. But you cannot, of course, you cannot access base from here, right? From under the wafer. So you have to put your lead here, so you can access emitter, base, and collector on top of the device. And so here are some parasitic that we have discussed. C mu, right, between base and collector, right? And CJE CJE just one part of C-pi between emitter and base. CB is not shown here, by the way. And I think the reason CB is not shown here is because it is even more distributed than CJE and C mu, so it's hard to fit in here. And between the real base lead, and the active region, there's a final resistance of RB, right? And between the collector, active collector region to the collector lead, we have finite RC. And the reason we heavily dope this region underneath the contact is to reduce the contact resistance. And another thing I want to mention is there's a buried layer here. Anybody knows why is it here? It's a buried M+ layer. M+ means heavily doped. So heavily doped reduces the resistance. So people dope this region just to reduce RC, because there's already a RC here. There's already RC3 here. We want to make RC2 as small as possible. Otherwise, this path is too long. So we need to heavily dope it to reduce RC. That's it. And the P, this is substrate too. Yeah, this P, these are all substrate, and this isolates this device and from another BJT devices aside. All right. Oh, okay. So this is the equivalent smart signal model of this device, MPN. CPI and RPI is across B and E. And there's a REX also. I forgot to mention REX, because from the emitter, less resistance from the emitter to the lead. And the emitter is normally it's pretty small, so this is rarely shown in small signal model. So CPI, RPI, and between B and C there's C mu and R mu. GMVB, this is the amplification. There's an output impedance R naught, and there's a from the collector to the substrate. There's a here collector to substrate. There's CCS. And by the way, these are the variables that I'm gonna use in SPICE. And this is this model is still not very accurate, because all the parasitics is not just lump elements. They are distributed, and they're distributed across each other. But this model is still adequate enough for low frequency calculations. For higher frequencies, there might be some error. There might be some error, and we'll talk about it later. And this is some other figures taken from a textbook, I think. Well, I've never seen it in Gray Meyer though. But it's essentially the same as this one. You have P substrate, you have N collector, P base. What? Okay. And N emitter. And this is the metal contacts, metal leads. And this is the top view of this BJT. And normally for each region, for each end, there are multiple contact points. The reason is obviously the reason is to reduce the contact resistance. I guess that's it for BJT. No, one more point. All right, so the reason we studied all these parasitics is because those parasitics is not very, it's not very important when the operating frequency is very small. But when the frequency gets higher and higher these days, those parasitics cannot be avoided, because that degrades the performance of the device in a big way. And one way to evaluate the performance of the device at a high frequency is to calculate how high the frequency can it go, while still giving us some reasonable performance. It's called unity gain frequency. So the definition of unity gain frequency is the frequency at which the current gain beta drops to 1. You don't get any, at that frequency you don't get any current gain. And the reason for of course why the current gain drops again is because of all those parasitic we have studied so far. So how to calculate? We need to calculate FT and see how is it related to the parasitic we've just studied. So let's take a look at it. Let's use this equivalent small signal circuit here. By the way, when we are calculating FT, we always use common emitter connection, which will be covered later on by Professor Nguyen. Current emitter, your emitter is ground, and also your collector is short circuit, it's DC ground. So you flow the base, they inject into the base current IB, right? And not all the IB is going to be amplified. Only only part of it. And the part of the base current that's going to be amplified is the part that flows through this input resistance, R pi. But because of C pi and C mu, not all IB is going to flow through here, right? C mu and C pi is going to take a certain amount. So we need to calculate how much current is going to flow through R pi before we can use those, before we can apply beta times IB, right? So V pi is the voltage across R pi. So R pi is in parallel with C pi and C mu, and we all know, parallel resistance equal to 1 over R pi plus SC mu and plus SC pi. So here's the voltage across R pi, and the collector current is equal to GM V pi, this part, minus, because C mu has take some current, but it's C mu's current flow this way, right? Flow this way, from left to right. So in order to calculate IC, you have to subtract GM V pi, subtract from GM V pi by S times C mu V pi. But since normally GM is much greater than SC mu, so we can still use this expression, IC equals to GM V pi. And so plug in the V pi expressions from here, we got IC equal to GM times this parallel resistance times IB. And so IC over IB, which is the current amplification ratio, current gain, is equal to GM over 1 over R pi plus S times C pi plus C mu. And apparently this is a low pass transfer function, right? Everybody knows low pass transfer function. So reorganize this expression, beta equals to GM R pi times 1 plus S R pi times C pi plus C mu. And therefore the corner frequency is equal to R pi times C pi plus C mu. 1 over R pi times C pi plus C mu. That's the corner frequency. But corner frequency is not what we want. Right? Corner frequency, let's take a look at a low pass transfer function. Corner frequency is here. It's the point where the current gain starts to drop. The unity gain frequency is where the current gain become 1. So we have to again plug in the frequency in so S equal to J omega, right? Everybody knows S equal to J omega. So plug in the unity gain frequency in this transfer function, and we let it equal to 1 to find the unity gain frequency. Therefore, we can find that omega t is equal to GM over C pi plus C mu, and therefore Ft equal to omega t divided by 2 pi. Let's see, omega b. So if you compare omega t and omega b, omega beta, omega t equal to beta times omega beta. So if you increase your current gain, your unity gain frequency also increases, apparently. Also, Professor Nguyen is not mentioned here. Once you got omega t, you can also calculate tau t, right? Tau t is equal to 1 over omega t, which is the time constant of this transfer function. And if you reorganize it, I believe in textbooks, Gray Meyer textbook, talk about this. Tau t is equal to C pi over GM plus CB over GM, which is not shown here. I don't know how to show you guys that equation. I don't have a tablet. Okay. Tau t is equal to 1 over omega t equal to C pi over Gm, Cv over Gm. Sorry. C mu. And Cv over Gm, as we have seen, is equal to tau f. It's the average time per carrier spent across the base, right? When we were discussing about C pi just now, we defined its parameters. And that's one basic constant for BJT. So it's T pi plus CJE over Gm, TF, sorry, plus C mu over Gm. And let's see, Gm, by the way, Gm is equal to IC over Vt, right? So when the collector current is very high, Gm is very high, and these two parts can be neglected, so you end up getting tau t equal to tau f. But when the current is very small, these two terms become much larger than tau f. Then you can imagine tau t drops. So tau t is related to your bias collector current, and the relationship is about like this. It's not monolistic. It's not monolistic as we've seen in this equation, because when static collector current is very large, there are some other effects which we didn't discuss here. Effects such as Kirk effect and high-level injection effects. So you guys, if you guys are more interested in this stuff, you can refer to, I think, 130 stuff, which talk about some more device physics. So anyway, and when the static current is very high, you can approximate tau t to tau f. So once you know tau f, you can approximately calculate a unity gain frequency. All right, so that's it for BJT. And now let's take a look at MOSFET, which is more widely used in current IC design, especially in digital some low power devices. So there are two kinds of MOSFET normally, NMOS and PMOS. And here, Professor Nguyen give you a cross-section view of I think it's an NMOS. Yeah, sorry. Yeah, NMOS devices. And NMOS is fabricated on P substrate again. It's fabricated on P substrate, and on top of the P substrate, there's this part is oxide, and this is gate. On top of the oxide, there's a gate material. There's a gate covered by it, covered on it, and the gate is normally made by metal or polysilicon. So that's why it's called metal oxide and semiconductor MOS, right? And on both sides of the gate, there are two regions, heavily n-doped, which give us source and drain. And of course, on top of the doping area, there is a metal contacts too. And on the right is the equivalent circuit model for NMOS, MOSFET, gate, source, drain, and substrate contact. And the reason why we use substrate contact is to tune threshold, and we'll discuss it later on. So I'm pretty sure these are all covered by 105, right? So here I just want to go through some basic equations to give you some reviews, which would be useful in later circuit designs in 140. All right, so let's take a look at the IV curve. There are two IV curves that we will use in 140. First is ID over VDS, and as VGS goes up, right, the curves also goes up. And there are two regions, linear region and saturation region. When the VDS is higher than VGS minus VT, then device operates in saturation region, right? And there's another IV curve is between ID and VGS. And when the device is biased above the threshold, then the drain current takes off, and it follows the quadratic relationship between VGS and VGS minus VTH. By the way, VGS minus VTH is called overdrive. Right? Everybody knows that, right? Overdrive voltage. Oh, okay. All right. So we still need to discuss different regions of a MOSFET, although it might sound boring, but somebody may already forget. So a cutoff region, gate current, of course, for all regions now here we assume gate current and gate current IG and the body current IB equal to 0 for simplicity. So for cutoff region, when VGS is smaller than VT, you don't have any drain current, obviously, unless you have a lot of leakage. When leakage is very apparent, or it's a big issue when a device is scaled down, and that's another kind of issue. You may see that in some other advanced digital circuit class like 241, 141. Okay, so cutoff region in here, we just assume ID equal to 0. When you gradually increase VGS, then you hit linear region. Linear region is where VDS smaller than VGS, smaller than overdrive voltage, and the ID, the drain current the expression end up being like this: mu n Cox W over L, VGS minus VTH, minus VDS over 2 times VDS. And the reason is called linear is because the drain current is linear dependent on VGS minus VTH. We call it mu n times Cox times W over L as Kn for simplicity. And as you further increase VDS, you hit saturation region, which is the most common region we want to drive the device. And the drain current has a quadratic relationship between VGS and minus VTH. And lambda here is the channel length modulation constant. Right? This slope. This slope gives you lambda, and this slope also gives you output impedance. So if you do localization, ID equal to 1 over 2 Kn times overdrive square times this channel length modulation. And here, of course, mu n is the mobility of the channel, and Cox is the gate oxide capacitance per unit area. So if you want to calculate capacitance, you have to multiply this value by the area you have. And this is threshold deviation. Yeah, I think we'll talk about threshold in more detail, in greater detail in a later page. So we just skip this first. And here's some other views taken from the textbook. Also, is it an MOS? Not necessarily MOS. No, it's just a MOSFET. Yeah, this is NMOS because it's P substrate. And the reason it's called NMOS is because the channel is N-type, right? Everybody knows. After you apply VG above threshold, you create an inversion layer right underneath the oxide, and it's electron for NMOS, right? Okay, so he also want to talk about PMOS, but the way you analyze PMOS is essentially the same as NMOS. You just flip the source and drain, because in PMOS the highest potential is applied as source, while in NMOS the highest potential is source is not always grounded, but always the lowest potential, and drain has the highest potential for NMOS. So the way you differentiate different regions are the same. You just apply absolute value on the parameters, then you can use the same equations or use the same expressions from NMOS. Yeah, threshold voltage. So we mentioned about in this video, we mentioned about the body contacts of MOS devices, but we didn't mention why this is there. The reason why we apply a body terminal there is to change the threshold, because again it's all kinds of devices. Basically, they are all p-n junctions, right? N plus region, p substrate, so p-n junctions. Then you have depletion layers, right? And once you apply voltage on one end or the other end, if you either forward bias or reverse bias the p-n junction, then you change the depletion layers. Then you change the charge in the channels, and in the end you change the threshold. Because all you have to do is to inverse the, to make a strong inversion under the oxide. So the charge changes will finally result in a threshold change. So this is the threshold expression for the NMOS device. For the MOS device, I don't want to go through too much details, but here's some basic definitions of the terms in this expression. Phi ms is the work function difference between a metal and semiconductor. Right? In order to make a device to work, you have to get through that first. You have to go over the work function difference first, right? Before you can reach the semiconductor. And phi s here is equal to 2 phi f, where phi f is Fermi level. Normally it's about 0.3 volt per silicon. And phi QB is the depletion charge. It's a depletion charge that you get in the p-n junction here. P is the substrate and n is the source and drain. By the way, and then QSS is the in NMOS QB is electrons, and so you have to apply a negative sign in this expression in order to get it right. And QSS is the charge trapped under the oxide. It's not controlled by bottom plate voltage. It's induced during the process, but it actually exists. So you have to to calculate the accurate threshold, you have to consider it. But it's positive sign here. So there is a difference between this expression and the expression you will see it in Gray-Meyer textbook, chapter 1. And the reason is in Professor Nguyen's expression, he always gives those charge and and potentials signs. For example, QB here, you have to apply negative because it's electron. You have to apply negative signs. And if you apply negative sign, it becomes plus. But in Gray-Meyer's books, they always use absolute values. So there's a minor difference between these two expressions. But if you use it correctly, you end up getting the same answers. So the place you can change the threshold, the place where the place where the bottom plate voltage comes into place is this term QB, because this is a depletion charge. And depletion charge is equal to square root 2 QES times MB 25F plus VSB. There we go. VSB takes effects in here. So once you increase VSB, I guess. Yeah. Once you increase VSB, your threshold voltage will also increase. Yes. Here's some more details about threshold calculating equation. So when VSB is equal to 0, the QB expression reduces to QB0. Right? So there's no VSB in here, only Fermi level, 2 times phi f. But when you gradually decrease the bottom plate voltage, then you in the reality you increase VSB value. Or you decrease B, so VSB increase, then your threshold voltage increase also. And you have to be aware here also this expression here, gamma for NMOS is negative again. So this is a little bit confusing. So Professor Nguyen, add these tables for you guys to understand better. For NMOS, gamma is negative. So when you increase VSB, threshold increases, not decrease. Yes, the depletion charge is negative for NMOS. Fermi level is negative for NMOS also. But if you're more used to the equations in Gray Myers textbook, you're free to use that too. Just to keep in mind, what kind of charge you are getting. All right, having seen the MOS devices, let's take a look at again small signal models, which will be quite frequently used in your study in the future. So this is the symbol of a NMOS device, and this is the equivalent. This is the equivalent circuit model. I believe you've all seen it in 105. And let's calculate some of the parameters, key parameters, not all, but some very important parameters. First of all, of course, it's GM, right? Amplifier is also all about GM. So GM is equal to partial ID over partial VGS. So plug in, we assume this device is operating in saturation region. So plug in the drain current equations and do the derivative. GM is equal to mu Cox W over L times VGS minus VTH. So, or in other words, V over drive. And there are two kinds. Yeah, you can write GM in different kind of way. Just play around. Write VGS and VTH out of ID, then you get this kind of equation. You only use ID and Kn. No big deal. And take a look. If you take a look at this small signal model, you should be aware of another GM, which is called GMB. Because when you change the bottom plate voltage, you also change you can also generate the transient conductance. It's called Bolton transient conductance. And again, by definition, GMB is equal to partial ID over partial VSB, or VBS. It's defined to partial ID over partial VBS. So if you want to use VSB here, because our threshold calculation, we always use VSB. But the definition of GMB, positive GMB, is partial ID over partial the BES. So you have to add a negative sign here. GMB equal to negative ID over VSB, and if you do the if you look at this one, if you look at the equation, you don't see ID depending on VSB, right? But it's related to VTH, and VTH is related to VSB. So that's how you can relate ID and VSB. So you do the partial ID over partial VTH first, then you do partial VT over partial VSB. And partial VD and partial ID over partial VTH is the same as GM, because in this equation VGS and VTH, you can flip the position of them, right? So the derivative should be the same. So partial ID over partial VTH is equal to partial ID over partial VGS, which is GM. So your GMB is equal to GM times something, right? And GM is the first part here, and the other part is partial VTH over partial VSB. And plug in the threshold equation we have just seen on the last page. You end up getting this parameter eta. So your GMB is equal to eta times GM. Now you relate GMB to GM, which is more convenient for your calculation. So when your bottom plate voltage drops, so VSB increase, your VTH increase, right, as we have just seen. Then your eta decrease, and so your GMB decrease. Another parameter is output resistance or output conductance. This is due to the channel modulation effects, as I've seen. As saturation region, when you gradually increase VT, you still get not much, but still getting larger drain current, and that's because there's an output impedance there. And by definition, GDS is equal to partial ID over VDS. Again, plug in the quadratic equations. You get GDS equal to lambda times ID sat. By the way, ID sat is the drain current, without considering the channel modulation effect. And so ID sat is equal to ID divided by 1 plus lambda VDS. But lambda VDS is normally it's smaller than 1, so we still approximate GDS equal to lambda ID, and so your R naught is equal to 1 over GDS, right, and equal to 1 over lambda ID. So if you know lambda, if you know your bias current, you can approximate your R naught. All right, so after we go through the basic parameters for the small signal models, as usual, we need to take a look at parasitics, which is useful for high frequency analysis. So take a look at this cross-sectional view of NMOS MOSFET again. On top of the P substrate, there are two N+ regions which give us source and drain, right? And this doping is made by ion implantation, right? Ion implant and the dopants, and then drive in deeper to the substrate. And this is done after oxide. After this is oxide. After oxide and metal or polygate is defined, right? So you first get these two stack patterned, then you inject ions, you implant ions into these two regions. And where ion implantation, there is you cannot implant ions fairly straight. There is a lateral diffusion. So there's going to be an overlap between a gate and source, and also gate and drain. And this overlap will give you, right, this is one plate, this is another plate, this is oxide, will give you a capacitance, of course. So this is called COL, it's overlap capacitance. This is a COL on the source side, and this is a COL on the drain side. And there's a depletion, and this is depletion layer, depletion regions, right? And P, there's a depletion layer here. Yeah. And there's a depletion capacitance, CD, but it will be shielded. It will be shielded by the inversion layer once the device has been turned on. So the capacitance here, the only capacitance we need to consider is CG. No, CG, CG. The capacitance between this metal plate and this another plate. This plate is not it's an inversion layer. We can think of it as another plate of the capacitor. All right. So here's the cross-sectional view, and this is the top view of the N MOSFET. So P substrate, P substrate, P substrate, P substrate, right? And this is doped N plus region as drain, and this doped N plus region as source. And this is the interconnects that defines the gate. And beneath gate is the channel, right? And LD is the lateral diffusion length, as we just discussed. And because of the LD, we form C over L here and here, right? And normally, so this lambda is different from the lambda we have seen just now. The other lambda is the channel modulation constant, channel length modulation constant. And this lambda is half of the minimum features in a circuit. Like if your technology, let's say 90 nanometers or 60 nanometers, then your lambda is half, 45 and 30 nanometer respectively. So so normally your minimum length is 2 lambda, and this is just a normal design. You can of course you can choose different kinds of. You cannot be smaller than this, but you can do larger, and also source and drain region you can do larger too. Here's just one example: 2 lambda for the minimum length, for the gate length, and 5 lambda for both source and drain. So now, having seen this top view, now we can calculate the capacitance between source and drain, between gate and source, and between gate and drain, right? So between gate and source, we call it the capacitance CGS, C gate and source, right? First of all is the overlapped capacitance COL, and second of all is the gate capacitance between the gate and the inversion layer. So COL we can COL is equal to LD times W times Cox. Right? Cox is the capacitance per unit area. So you have to, in order to calculate COL, you have to calculate area first, lateral diffusion area. So that's COL. And the capacitance between gate and the inversion layer is 2 over 3 W times L effective times Cox. So L effective is the minimum, the channel length minus minus 2 LD, because 2 LD on both sides. The reason there is a 2 over 3 is because at saturation, the inversion layer is not flat under the oxide. It's pinched. There's a slope, so you have to integrate over the channel length. And after you do the integration, end up it gives you the 2 over 3. And this region is when it's highly saturated. This region there's no charge, pinched. And for the gate to drain, it's easier because you don't have any, you barely have charges here. So CGD is just merely equal to COL. And COL here is equal to COL there, because your lateral diffusion on both sides are exactly the same. Let's see, CSB and CDB. Oh, okay. So take a look at this. Right, that's the capacitance associated. The capacitance we just discussed are also associated with the gate, but we also have capacitance, associated to the substrate. From source to substrate, from drain to substrate, right? So we need to calculate also CSB and CDB, source to bulk, and source to body and drain to body. So think of the source and drain as a well, right? So a well, you have sidewall. You've seen a 3D, you have sidewall and you have bottom, right? And the way you calculate sidewall and bottom capacitance are different, because at this region at the bottom of the well is not highly doped. It's just substrate. It's not highly doped. But on the sidewall here and there, it need to be P plus. The reason for that is to isolate this device from the other device. So there's no interaction between this device and other device, and also there's no interaction between the source and drain of this device to some other interconnect wires. So this region has to be P plus, highly P doped. So different doping level will give you different capacitance value. So, but you don't have to calculate that. You don't have to calculate that. There's a starting value for you to calculate. So CDB is equal to, bottom. I think you already divided into two parts, right? This is bottom. This is the bottom junction capacitance, and this is the sidewall junction capacitance. So CJSW and CJ naught are the. I think they are different dimensions. CJ naught is the capacitance, the unit area capacitance of the PN junction at the bottom plate, and CJSW is the unit length capacitance. It's not unit area; it's the unit length capacitance along the sidewall. So if you look at this device, CJ naught, CJ at the bottom plate is equal to this area times CJ naught, right? So W times phi times L. So L is phi lambda. So here you got W times phi lambda times CJ naught. And CJSW, you only have three edges that has N plus and P plus doped. So W plus 2 times phi lambda times CJSW. Yeah, I guess that's it. So this equation will give you CSB and CDB should be the same. Or it'll be very close. The only difference might be, for drain, because normally for the NMOS device, drain voltage is higher than source. So your depletion layer width is a little bit different at drain and source. But in here, in calculating CDB and CSB, we treat them the same. Just to keep in mind. So the actual profile of the depletion layer should be like this. Right. So oxide. Let's see. All right, a little bit larger on the drain side because it's reverse bias. And the higher voltage you reverse bias it, the bigger the depletion layer. All right, so that's it. What's the time?